All right, so this is the second machine learning class. The videos of the first one are up. And so I just want to talk about chapter 2, which is the data processing necessary to get a machine learning project off the ground. So let me get the slides up. All right. So there, that looks pretty good. So we're just going to talk about the steps in the project. First, you look at the picture and try to plan what you're doing. Then you get the data. You'll need a large amount of data from somewhere. Then you're going to have to explore the data and visualize it in order to clean it up and see what you've got. Prepare it, select a model and train it, then fine-tune it, and then present a solution. And then you're going to have to launch and monitor and maintain your system. This step being pretty complicated. And like I mentioned last time, the British security model talks about this in useful detail. You have to track the errors, deal with the errors, get feedback from your users about what flaws it might have and such. So there's a lot of data repositories to practice on, many out there like openml.org, a bunch of government ones and so on. There's a lot of things that are standard used for people to learn machine learning, standard data. So we're going to take one of those data sets here, and we're going to model the price of California housing in the 90s because there is just such a data set. So in comes a bunch of data about people who live in California. And we're going to try and predict the pricing in each district of California. They've broken up into a bunch of districts that seem smaller than counties. And then they will presumably take other signals and use that to decide what investments to make in real estate. That's the idea. Now, we can use supervised learning because the data we're getting is labeled. It's going to include a real information about housing prices. And we're going to use regression, which means the model will predict a numerical value, and batch learning. We're going to train it all on a batch of data and have no additional data added later. So those are general system design decisions you make. Multiple regression uses multiple features. Univariate predicts a single value, multivariate predicts multiple values. In our case, we want to predict one value, which is the housing price, average housing price in a district, and we want to take many features in to get that value. Now, if you're going to do this, you're going to have data and some correct housing price, and we're going to try and predict the housing price from other data and have some measure of how accurate we are. So you choose a performance measure. And if you go all the way back to more than a century ago, I think back to Gauss, the standard error is this mean squared error. You take the predicted value minus the correct value, you square it and add it up. And this has two effects. In the first place, it's always positive. So predicting too high is bad and predicting too low is also bad. Also, large deviations are weighted more than small deviations by the square. So this is the standard error, and that's called the Euclidean norm, and they call it L2 because it takes the difference to the second power. Now, if your data is very noisy, has a lot of errors or a lot of deviation from the expected value, and you wish to tolerate that because then you might not want to emphasize large errors more than small errors the way this does, so you might use the Manhattan norm. And the Manhattan norm comes from a measure of distance on a grid. If you have a series of roads that are just a grid between north-south roads and east-west roads, and you want to count the distance between two spots, it doesn't really make sense to calculate the straight line distance because unless you're a bird, you're not able to travel in a straight line. Instead, you're just going to follow the blocks. So you just count the number of horizontal blocks and the number of vertical blocks and add them together. And that's what the Manhattan norm is. You just take the absolute difference between the predicted value and the real value instead of the square and add that up. That's L1. And this is going to repeat all through our future parts in this course. We'll talk about whether you should be using the L1 norm or the L2 norm as we go ahead. That's what they are. So here's our assumption. The price is a numerical value. This is important. Sometimes you don't have a real number. Like, if you have a medical interrogation or a psychological thing, they say, how bad is the pain or how happy are you on a scale from 1 to 10? So you get that, but that's not really a number. It's not really true that two twos can be added up and make a 4. It's just categorization. So if that's the case, and you have categories like cheap, medium, or expensive, then you're technically not doing regression. You're doing classification. And we'll do a lot of that. And like we talked about before, if you have a series of handwritten digits and you're just trying to decide which digit were you writing, 1, 2, 3, or 4, up to 9 with a 0, that's categorization because it's not true that somehow two calculations of 1 are equal to one calculation of 2 or anything like that. They're just categories. And often that's what you do. But we are here doing regression. It's dollars, or the price that really is a numerical value. So we get the data. Now we're going to do it. I'll demonstrate this a little later. You use a Python environment, which you can use the free Colab Google environment, and then you just execute some code which will download it from GitHub. This data exists on GitHub. It's housing data from the government. And when you get it, you can do info, and that will summarize it. And as you see, here's what we have. We have longitude and latitude, housing median age, rooms, bedrooms, population of households, median income, and item 8 is median house value. That is the number that we're trying to predict from all the rest, an ocean proximity. So the 8 is the label, all the rest are the input data, and the goal is to predict number 8 from the other data, and it's labeled, we know the right answer is. So import the data, and head will show you the first 5 rows, like I say. And this just shows that all these things are numerical values, except ocean proximity is an alphabetical thing, saying near bay. So that's a categorization for sure. And so if you print out its value counts, you'll see there are only 5 possible values. Less than 1H ocean, which I guess means near the ocean, something like that. And then inland, near ocean, near bay, inland, that sort of thing. So these are those are the categories of location. And describe will show statistics of each value, like mean and standard deviation and such, and it will only do that for numerical values, of course. It won't do it for category values. And then you can make histograms, which is very useful. Histograms give you a layout of the data, and in particular, you can see it's quite common for measures of statistical performance to assume that you have a normal distribution. Like this one here is a Poisson distribution, which is pretty close to a normal distribution. You have a peak, which is the most common value, and then you have an approximately equal distribution above and below that value. This skewing you see here is technically a Poisson, which is a small transformation of a normal. That's what you normally expect in statistics, is there's a peak and there's a sort of equal deviations above and below. But here we have some failures to be that. Like here, latitude and longitude are not at all that way, as you'd imagine, because in California we do not have an even distribution of houses geographically. In fact, we have a bunch of northern stuff near San Francisco and a bunch of southern stuff near LA and not much else. So it's a 2-peak distribution. And the housing median age seems to have a whole series of strange peaks. I would imagine this is suggesting that there were just waves of times when people have built houses in California, like some kind of wave in the 80s or 90s that makes them 20 years old. I guess this data is from the 90s. This would be some kind of build in the 70s. This would be some kind of build after World War II or something like that. And another thing that's really disturbing and going to come back to us a lot is notice this huge spike at the end. I don't believe it's true that there are some enormous number of houses that are exactly 50 years old in California. I think this means that when they measured this number, 50 was just the largest available number. So this 50 really means 50 or bigger. And that is a problem. That means that this numerical value is not really a mathematical smooth numerical value. Over here, it's just a category. And that is a problem. A simple categorization task is not going to be accurate, and a numerical regression task is not going to be accurate either. And we're going to see this a lot as we go ahead. There are problems in the data which we have to deal with, and if we don't correct them, your model is going to have errors caused by the data not really being structured the way it should be structured. And this is extremely common because when you get real data, it's the way somebody measured it, and often that is not the way a machine learning model needs it to be. And you're going to have to correct or modify it to get it into a format where the mathematical structure of your machine learning model makes sense. Now we're trying to predict the median income. It's somehow been scaled and capped at 15 max and 0.5 min. The numbers are approximately numbers of tens of thousands of dollars. This is not necessarily bad. You can have preprocessed data. In fact, as we'll say, you very often normalize data, so it goes through some specified range like -1 to 1 or 0 to 1 in units to prevent one dimension from being weighted far more important than another dimension. So that should be okay, but there are capped values. Age and median house value were capped. So that means, in fact, if you look, the value is super important. This is what we're trying to predict, and notice it has the same problem. There's a reasonable distribution and then a huge spike at 500,000. So again, this number is not really an accurate measure of 500,000. It's 500,000 or more. And that we're going to have to deal with. All right. So what we're probably going to have to do is just remove all that data at 500,000 and the other data at the peak because we know it's wrong and we don't know how to fix it. So we'll probably have to remove that data, which is just misleading the model. All right. Now another thing is the attributes have very different scales. If you go back here and look at it, the latitude and longitude latitude goes from about 30 to 40, longitude goes from -114 to -124. The age goes from 0 to 50. The median house value goes from 0 to 10,000. These are all in wildly different scales. And if you leave them that way, when you do something like calculate the mean square, you're going to be counting the big numbers far more than little numbers. It's going to be a problem. So you kind of need to scale them. We'll transform them to fix that. Another thing, by the way, is you saw the histogram skewed right like Poisson distribution. We'll probably want to transform the axes into an axis that makes it look like a more normal Gaussian to have the model work right. And so the other thing, when you get your data, you take 20% of the data and set it aside and don't use it to train your model. You can either randomly select that data or do stratified sampling because you're going to train the model on 80% of the data, and then you're going to test it by showing your model this 20% test set that the model has never seen before. This is real important because you want your model to learn the real trend of the underlying phenomenon of which you have samples. You don't want it to memorize the training data and only work on the training data. So you want to train it on data, and then you want to test it with new data drawn from the same population, but that the model has never seen before, and accuracy on that is what you'd really like to achieve. If you do random sampling, then this is obviously likely to work if you have a large sample, but there's a flaw that can happen here. Suppose we're measuring something that is different for men and women, like say life expectancy or a chance to get a certain kind of cancer or something. So real population is 51% female in America. If you take a random sample and you'll find that there's a probability that you might get 54% females or only 48% females just in your random sample. And if your test set is like that, then it is skewed and not representative of the population in an important way. So a better solution is stratified sampling, where you bin your data into bins and you draw enough random samples in this category to get the right percentage in each of these, so you make sure that your test set has percentages matching this thing. Instead of being randomly drawn completely independently, you choose random amounts out of each bin. And that makes sure that your test set is not biased in an obvious way against an important parameter. That's called stratified sampling. So let's try Kahoot. I should have them here. And the big lesson of this chapter for me is that it's a lot less scientific than I thought it was. It's a lot less automatic than I thought it was. And I was thinking a lot about the prediction of election results as I read this, that you would think, you just ask a bunch of people who they're going to vote for, and you can predict who's going to win. But instead, you have a whole bunch of human judgment of how you're going to correct for all these various errors in the data you have. And that means it's not like just a machine where you feed in data and out comes the answer. It's far more complicated than that. And let's see if I can find my ML chapter 2. Seems to be strangely missing. There it is. Okay. It just doesn't sort in order the way I think it should, but that's life. All right. All right. All right. So if the data changes frequency and is unlabeled, what learning method should be used? You got it? Unsupervised and online. Unsupervised because it's unlabeled, and online so it can keep relearning because the data changes. All right? Okay, what performance measure is best if you have many outliers? Not liners, but outliers. All right. MAE, which is the Manhattan distance, I think, is what we're looking for. Not the root mean square, but the mean absolute error. Someone named Warrington asks if I got an email. No, I haven't seen any emails in a while. All right. All right, so what sampling system avoids introducing bias caused by bad luck? All right, that's stratified sampling is what prevents that by carefully choosing a representative portion of each of the main categories of data. All right, and so IDK is going to be one of the winners, I know. By the way, IDK, I see you in my classes that count for college credit, and I don't know who you are. So if you want your points, you're going to have to tell me who you are at some point. But if you don't care, that's fine. All right, anyway, let's carry on here. All right, so now we're going to try to find insights from the data here. So the scatter plot, if you plot latitude versus longitude, then you'll see what data exists, and you get a sort of trace out of California. But this scatter plot, in fact, there's no way to tell how dense these areas of dense dots are, so that's not a very good visualization. So it makes sense to add transparency to the dots so you can see how dense the dense regions are. And you could also add another variable with colors. So here they add the price with colors. You can see that, in fact, the houses inland are cheaper, and the houses in the dense areas of San Francisco and Los Angeles are much more expensive, as you'd expect. And now you can try doing correlations. Now we're trying to predict the house value, so you can calculate a correlation coefficient. And of course, house value is 100% correlated with house value. Any number significantly far from zero means that variable helps predict it. And so you see median income is very predictive, about 70% correlation, which makes sense. The people with higher income will live in the area with higher house values. Total number of rooms is only 13%, 10%, pretty small values. Looks like latitude has some predictive power, but nothing too great. So you see which variables are useful. These variables here are less than 10% predictive, so not very valuable at all. And you can make a scatter matrix showing how the house value is predicted by other things. Here's just the distribution of house value, and here's the prediction between income and house value. This is what a strong correlation looks like. As the horizontal number gets bigger, the vertical number follows it, and you have a nice line there. Here you have a little bit of a trend. Here you have basically no trend at all. And by examining these, you can get a visualization. Here's another view of income against house value, showing this thing just turned around with the X and Y reversed. All right, so median income, the correlation is strong. But if you examine it carefully, you'll see some weird artifacts here. One thing I mentioned before, there's a huge cluster of dots at $500,000 of house value, which is not a real thing, not representative of the underlying population. And there seem to be other round-off errors, like a spike of data at 350 and 450, suggesting that some of this data is not an accurate measure, but somehow rounded off into categories. So we're going to have to either remove these data or try to replace them with data we average from the data around it, because you don't really want to train a model to reproduce these spikes unless you believe those spikes actually represent what's in the real data. And this is where I really get sort of a queasy feeling. My years as a research scientist, I wouldn't want to impose my judgment on the data. I'd say the data is what I measured, that's what's real. But here, your measurement technique has errors in it, so you have to insert judgment. Do you believe there's really a large population of houses at this value more than above and below it? Or do you believe that's an artifact of the data and you're just going to have to make a decision, since it's too expensive to go get your own data and use a superior technique of gathering the data? You're going to have to make some kind of human judgment about how much of this data do you believe and how much of this data do you decide to throw away because you think it's wrong. And now I think I get a much greater insight into how, a bunch of different people can do a poll saying who's going to win the next election. And some of them will say this person's going to win, and some will say that person's going to win. Even though it seems like they both measured the same kind of data from the same population, they made different judgments about how to massage and modify the data. Even if they are doing the best they can, they kind of have to insert human guesses into the process here. So we talked about correlation. That's 100% correlation. Here's 80 and 40% and so on. Here's some uncorrelated things where, in fact, in principle, you are learning something about the vertical value from the horizontal value, but if you're trying to just fit it with a straight line, a line is not going to fit. So you can, now another thing which is interesting is, since you have many parameters you've measured about the population in this area, you're trying to predict the house value from, they are not independent. So it's not like you have completely independent measures. They're connected. So you could try combining things like rooms per house, total rooms over total households, how many rooms are bedrooms, how many people are in the house. And since you've done that, sometimes these composite combinations are more predictive than the ones underneath. Like here, the bedrooms ratio is very predictive, 25%, far more than any of the things themselves. So here's another thing that wouldn't happen with simple cases where you're measuring normal statistical independent things like, voltage and pressure and stuff. A combination of these might result in something that's more useful because it cancels out the noise and amplifies the signal. So that's another thing you do. And we're going to do quite a lot of that as we go forward, making composite new attributes out of the original attributes. So now you got to, like I say, you got to clean up the data. You've got to either get rid of the districts that have a deviant information, get rid of the whole attribute, or set the missing values to some value that's not going to mess it up. Like I was saying, your choices here are to either just remove the data at 500,000 and 450,000 and 350,000, or adjust these to just be what you expect them to be, or some harmless value, that sort of thing. Or just quit using this entirely, which would really be pretty bad because income is our main predictor. So in this case, you'd probably just remove them, I would think, but you might just move them to what you see as the center of this. Those are distortions in the data, but they're moving it closer to the actual meaning of the data as far as we can tell. Okay, then you got problems like handling text and categorical attributes. Your ocean proximity just has these alphabetical descriptions. It's not a number at all. So what do? If you replaced them with numbers, then you could just call it 1, 2, 3, 4, 5, but then the machine learning would somehow try to say that the distance between 1 and 2 is smaller than the distance between 1 and 3, and that's not really true. So what the best categorization is what they call one-hot vectors. You add 5 parameters, 5 attributes, and each one of them is one in only one space. So this one is in category number 4, this one's category number 1, this one's category number 2. So now you've taken one measurement, you've turned it into what you regard as 5 independent measurements that are essentially Boolean. This is a way to mathematically represent it that captures the meaning. It's a categorization, but it does not create a number where you can have any implied numerical relationship between them. Just you're in this category or you're in that category, but you're not somehow, some way, like 2 of these would add up to 1 of those or anything like that. That's called one-hot vectors. All right, and so number of rooms scales to 39,000, income goes to 15, and so on it goes. So to prevent this, there are common ways to scale it. Just scale everything from 0 to 1, or scale everything from -1 to 1. So subtract the mean, divide by the standard deviation. That's another way to do it. That doesn't strictly make it go from -1 to 1, but it prevents it from getting very far from that. So these are ways to make the various parameters have equal weight. Then you got this Poisson distribution where there's a heavy tail. The upward region is much bigger than the lower region. So there are various solutions. You could take the log of this or something to make it even. That's one way to go. Or you could just bucketize it, turn it into a categorization problem where you just take how many are in different buckets. These are various ways to handle that kind of data. All right, so then you select a model. Linear regression is a simple one. And if you do the linear regression, you're going to get a prediction. And the first prediction is going to be off by an enormous amount. These are the predictions. These are the labels. So it predicted 243,000, but the actual number is 458,000. So this is drawing a straight line through something that is not really a straight line at all. So that's not very good. All right, so those are really bad predictions. And so a more powerful model is a decision tree, which we'll talk more about in the future, a whole lot of if-then statements. And all right. So you can train your model and see how much its value. Zero error suggests overfitting. Error shouldn't be zero. And so you can do a better form of evaluation with cross-validation, split the training set into 10 folds, then train the model 10 times. You train it on 9 of the folds and test it on the remaining one, and you do this for all combinations. And then you get a result that's still very bad. Your standard deviation is, I'm not sure how we can see that it's bad, but hard to read these numbers, but according to the book, it's as bad as the other one. And when I look at this, I see the standard deviation looks pretty low, but I don't see the error here. But they say the error is, in fact, very bad. Anyway, so the random forest regressor will be somewhat better. On the test set, it was 47,000 off. But on the training set, it was 17,000 off. So that still that still shows that we're doing overfitting. We are modeling the training data far better than the test data. And that's a sign that we're fitting not only the trend in the data, but also the noise. So we can fine tune the model. There's a thing called a grid search, which will add hyperparameters. This is what you do. If your model is too good on the training set and too bad on the test set, then it is following the noise in the data, so you add a regularization parameter to smooth it out, to cause it to draw a smooth curve through the noisy data instead of fitting the noise. Therefore, it will be less accurate on the training set, but hopefully more accurate on a test set. So that's when you add hyperparameters. And since you don't know what value to use for the hyperparameters, you do a grid search trying many values. That's one common solution. Another is a randomized search, where you try random hyperparameter values until you get the best results. And you can also combine several models together to hopefully get the best features of all of them. Now, those are various techniques. So then you deploy your model, perhaps as a web app to be used for something like your investment people to make decisions, and then you measure to see how well it works. Monitor its performance. Now, if something changes in the real world, like there's, say, an economic crash and the financial truth of the world changes, and your model was trained before that, then it will suddenly be a less representative model of the world. It might gradually rot as the world gradually deviates away from the situation you trained it on. One measure would be your downstream metrics. How successful is it in business? Or you can send human raters, samples of pictures it's trying to read, see how accurately it gets it. It can be difficult to set up performance monitoring, but you really have to, because your model is not perfect, and it may have systematic disturbing problems. This is something I raise a lot in my consulting with people who are almost all deploying large language model things now, like customer chatbots. And I say you really have to have some opportunity for customers to give you feedback, saying the chatbot told me something terribly wrong, like it promised me a discount and then I can't get the discount. You have to have some measurement of how often that is happening, because there's strong evidence that that sort of thing does happen. And if you're not looking for it, you won't know about it. And you want to know how often that happens and if that probability is increasing or decreasing. So you can update and retrain it, collecting fresh data, retraining it in various ways. But it's kind of a new field, and you want to keep copies of all your models. You may have to roll back, especially when you're doing early pilot rollouts of new things we really don't understand, like all these large language models. They're new, they have strange defects and errors, they keep changing. We really don't thoroughly understand how they work and what sort of mistakes will come, so you do need to have some feedback process to find out what went wrong. Anyway, let's try 2B. All right. All right. All right. I think these are the only two playing the Kahoots. All right, so which method assumes a linear relationship? All right, that's what a correlation is. Measures how well one thing is linearly related to another. All right. Which method uses these semi-transparent graphical elements? I thought that was a scatter plot. Apparently they called it a scatter matrix. I wonder if I can tell that from the slides. I remember seeing it. It was back here. This is the scatter matrix. And those are not semi-transparent. I think this one's wrong. This one here, that's the scatter. Oh, that's the scatter plot. And this is a transparency scatter plot. So I think that one's unfair. I'll try and make a note to fix it next time. I can't change it now, but I think that should really be scatter plot. Let me make a note, chapter 2B. Bad answer. All right, probably just remove that question. Anyway, on we go. Part of the reason why these things are extra credit is sometimes they are not as good as I want them to be. All right, which system fills in a missing value with a typical value? Yeah, that's called imputation, where you have something like that 450,000 where I have, it looks like the data I've got is wrong. So instead I've replaced those data values with the expected value. That's called imputation. All right, and which one splits the data into folds to measure its performance? All right, that's cross-validation. Fair enough. So anyway, it's going to be the same two people winning for what it's worth. All right, and we stop this recording.